So before this, we talked about combinational circuit. So combination. Now we'll be talking about the sequential. So we'll be talking about sequential logic. Basically, we'll create our own processor from scratch. Okay, that's the goal. This is very exciting. All right. So first of all, before I proceed to the sequential circuit, I want to go over some, fundamental concepts. Okay. So let me define the sequential logic. So what is sequential logic? It consists of a logic circuit whose output depends on the input. Output depend on the their value at the previous time. Suppose. So at t equals I don't know, t equals t equals t0. So output at t equals t depends on the output at t equals t0. Okay, so it's time dependent now. Time dependent. So your output depends on time. Okay, because it depends on time, meaning so it remembers the previous value, right? If it remembers the previous value, that's why our output at time t depends on previous value. That's what I'm trying to say here. Okay. For instance, if you have a counter, right? Very simple example, or stop clock, stopwatch, for instance. So what he does is just he starts at 1, then he adds 1 more to it, so it becomes 2, then add 1 more to it, then becomes 3. So then add 1 more, because it has to remember the previous, right? So then add 1 more, it is 3. When it is 1 more, then it is 4. Okay, it just has to depend on the previous one. Okay, when I say 1 more here, this is 2. When I say 1 more here, this is 3. When I say 1 more here, this is 4, right? So meaning it depends on the previous value. So output is time dependent in that case. So we'll talk about this kind of circuit now, which are called sequential logic circuit. Sequential logic. So mainly the time-varying logic, time-varying devices are of mainly 3 types. So bistable, monostable, and the third one is astable, right? So mainly 3 types of time-varying logic devices. So bistable. So when I say bistable, it's like the device can be in either, because when I say state is 0 or 1, right? So this is 0 state, this is 1. A device can be in either 0 state or 1 state without no problem. Okay, if you put it here, it will be there forever. If you put it there, the stuff will be there forever. Okay, that's called bistable. For instance, your light switch, right? If you have a light switch, this is just a mechanical device, but this will make sense. Okay, even though we are talking about digital, we can understand how it works by the help of mechanical device as well. So if you have a light switch, you have on and off. When you turn it to on, right, then it stays on forever. When you turn it to off, right, then it stays off forever. Okay. So this is on means 1, off means 0, right? So this kind of device is called bistable device. Now monostable means it is stable only at one of the states. Okay, let's say here, either that guy is either stable here or stable here. It's or. Meaning, suppose this guy is stable here, right? Suppose this is stable here. Meaning, if you want to change it to this location here, if you bring it back to here, you could do it momentarily, but it will come back to this state again. Because this is your stable state. This is your stable state. If you want to change it to other state, then after some time it will go back to the stable state again. That's called monostable. So let me give you an example of monostable. So here, now this is the switch, right? This is the switch here. Okay. So if you have a switch here, what is the tendency of this switch? To stay off. The tendency of this switch is stay off. Okay. So, but somehow you want to change it to on, right? Okay, you just pushed it, so it is on. Okay. Then what happens is after some time, it will come back to off. You see that? So this guy pushes the switch, and you can see the light glowing here. This light up. But after some time, it comes back again because the stable state is off. So stable state is off. That's why even though you turn it on, it comes back to off state again. That's the monostable device. How about astable? Astable meaning it changes the states spontaneously from one to the other. Okay, you don't have to do anything like here, right? What is this guy doing? It is off and on spontaneously, right? You don't have to do anything. See, it's off, on, off, on, off. Okay, spontaneously. That's why this kind of device is called astable. Guys, question here so far?
Is this what our lab is going to be on Wednesday?
No. So we'll have a lab here, but in maybe a couple of weeks. So the next lab is relatively long. So it might take 2 to 3 weeks to finish the lab. So that lab is based on chapter 4, not 5. After we finish that, then we'll have a lab based on chapter 5.
Gotcha. Thanks.
All right. So some other definition also. So so here I'm going to talk about positive edge transition and negative edge. So I'm going to define two terminologies here: positive edge and negative edge. Okay, so those are the transitions. So positive edge transition you can call L to H, low to high, and this transition you can call high to low. Okay, so before we understand this positive and negative edge, I want to recall a concept that we discussed before. What is propagation delay? So we denote this by Tpd, time propagation delay. So what is that propagation delay? So the time it takes for a transition to occur through the gate. Suppose you have a gate. I don't know, it could be any kind of gate. Okay. So how long it takes for this signal? Suppose you have signal here, right? You have signal here. This is digital, right? So why did I do? This is signal here. This is high. This is high. So suppose you have a signal here. Then for these signals to pass through this gate, it takes some time, right? Here, it takes some time to pass it through to pass through the gate? What is the time it takes to pass for the signal to pass through the gate? That time is called propagation delay. Okay. So depending on the device we choose, the propagation delay is different. So some devices have a smaller propagation delay, some have bigger. So here, if you consider 74, by now you must be familiar with this device chip, right? 7400. So this has the propagation delay of 7 nanosecond, and this device has the propagation delay of 15 nanosecond. So even though we call it 7, so the propagation delay depends on temperature and also gate to gate. Okay, so I'm talking about just one particular category of gate here. Suppose you are talking about the 7400, right? This device, we call it 7 nanosecond. If you heat up this device, right, the propagation delay might change. And also, so one chip, so one 7400 chip might be different from another 7400 device chip, okay? So which is different from the third one. They don't exactly match, even though we call 7 second could be 6.9, 7.1, I don't know, okay? 7.5, 6.5, its average is 7. So it depends on temperature and chips to chips. So that's why it's very tricky. But we'll do something for it. So before now, now let me go back to positive edge transition and negative edge transition. What is positive edge and negative edge? So you have, so what is this signal here? You have 0 here, low signal up to here, then it goes to high, okay, and then it goes to low again, then it goes to high again, then low, right? So here it is low, then high, then low, then high, then low, then high, then low, right? So here, what is the positive edge and what is the negative edge? That's what I'm trying to show you here. If you look at this guy here, okay, so this is negative edge and this is positive edge. So positive edge meaning when it goes from low to high, this edge is called positive. Okay, low to high. So this is low, this is high. So this edge here is called positive edge. However, this edge is going from high to low, right? So this is called negative edge transition. So we need this in the next couple of slides or so. All right, so we talked about propagation delay, right, last time. So in the last slide, propagation delay. So why do we need this concept? Because so we need to understand, so what should be the frequency of the input signal? Frequency of input signal. What is the minimum frequency? Sorry, what is the maximum frequency I can have here? What is the maximum frequency I can have? So maximum frequency you can have here is defined by Tpd. Why? Because suppose you the Tpd here is 7, right? Let's say 7 nanosecond. Okay. So what is the frequency of what is the frequency related to 7 nanosecond? How do you relate the frequency with the time? 1 over t. If you calculate this guy, what do we get here? 1 over 7, 10 to the negative 19. Okay. So you cannot have so oops, so okay, so you cannot have the signal, right? Frequency means what? It changes up and down, right? So how fast the signal changes is high to low, right? How fast, or low to high. Okay, that's the frequency, right? So you cannot have the frequency here bigger than corresponding frequency of 7 nanosecond. So what is the corresponding frequency 7 nanosecond? Given by this, right? So you cannot have the frequency here bigger than the corresponding value of 7 nanosecond. In other words, input signal cannot change in a time shorter than TPD. Okay, that defines your frequency. If you change quickly, then it cannot keep up with the change. If the change here is quick, very quick, then the output, what happens to the output? This output cannot keep up with the input, change in input. So that's why you have the propagation delay time is very important. So what you can do here is, suppose so if you want more propagation delay, right, then you can use more gates like here. Okay, so suppose you want signal, so your signal is passes through this NOT gate, but propagation delay here is less, right? Let's say 7 nanosecond. But you need that this propagation delay sorry. So where I was. So here, let me. So what I'm saying is, you can delay the input by using more gates in the circuit. Okay. So if you have if you want delayed input, then you can add instead of having two inputs like this, right? If you want to delay this input here, then what you can do is you can send, suppose this is your 1, then you get 1 here, right? So if it goes through here, this 1 becomes 0. This 0 becomes 1. Okay? So if you want, you can if you want 1 1, you can connect these two. If you want 1 0, then 0, this is 1 0 1 0, right? So if you want 1 0, you could simply have only one gate also, right? NOT gate also. But instead of doing that, you just put there 3 because you want delayed input. If you want delayed input, you can have more gates in connected like this. Okay, so that way you get the delayed input. Let's say you have the delayed input here, then what is the behavior of the circuit? How does this behave? Suppose this is the input. So this is the input you give here, right? This is the input you give here, like this. This is the input given there. So what is the delayed input here? So if this is NOT gate, right? So if this is 0, this is 1. If this is 1, this is 0. If this is 0, this is 1. Meaning your NOT gate gives the opposite of the signal here, right? Meaning if the signal is like this, then what is the input here? Help me.
0.
So yeah, I think I didn't ask the question properly. Let me ask it again. So if the input here is like this, so what is the input here? So this low does not get, right? You have 3 NOT gates. So this guy inverse once, this guy inverse once, then this way again inverse once, right? So you get the opposite input here, right? So that's why this is low, this becomes high. This becomes high. Then you get, this is high, you get low. This is low, you get high. But you can see slightly shift, right? Do you see the shift? They are not exactly on top of each other like this. They are not like this. Rather, they're like this. They're like this. So a little bit shifted to the right. So we have this 1 and 2, not 3. So we have 1 and 2, not 3. Because why is this happening? Why is there delay here? See, it means here delay. So delay. Why do I call it delay? Because here it should have been here, right? The change should have occurred at this time. Instead, the change occurred here after some time, right? That's why we call it delay. This is called delayed input. Okay. All right. So let's pass through now. What is the output then? In this case, what is the output? Let's talk about the output here. Okay. So up to here, up to here, up to right here, right? What is the input? 0. What is the output? What is another input? 1. Okay. Up to there, the input, one input is 0, other input is 1. What do you get? You get 0. Up to here, you get 0. Got 0, right? See, you got 0 here, up to here. Now, right here, what I'm trying to say over here is, now let me change the color here. Let me change the color. Okay, right here, oops. So from here to here, what is your input? Delayed input is 1. From here to here, what is your delayed input? 1. Do you see that? So during this section, you have 1 and 1 here. Then what is the output?
1.
1, right? So that's why you have 1. See, you have this 1 here. Okay. Then after that, let me change the color again. So after that, so what is the input 1? Input 1 is 1, right? What is your input 2?
0.
Until here is 0, right? Okay. So this is 0, this is 1. Then what do you have here? This is 1, this is 0. What do you get?
0.
That's why you have 0 up to here. Up to here, 0 makes sense, right? Now, yeah, go ahead.
Was somebody else going to ask a question? What is the purpose of this in a circuit?
Oh, I'm just trying to understand the so what is the This is called time diagram, okay? So this is very important in timing. It's called timing diagram, okay? So this is called timing diagram. So in the coming slides, we'll be talking about timing diagram a lot. Okay, that's, you need to understand timing diagram to understand the sequential circuit, okay? So that's why I'm trying to focus on this timing thing. So then here, from here to here, so what is the input one? Input one is 0.
0.
So from here to here, what is the input one? 0. And what is your output?
0.
That's why this is 0 also. Okay. Now let me change back to a different color again. So different, maybe green again. Okay. So then, what is my thing? Okay. Then from here to here, what do you have? 0, right? This guy is 0. Okay. Then what is this guy here? From here to here, 1. Then what is your output? 0. That's why you have 0 throughout. See, there is 1 right here, and except that, we have 0 everywhere else. Okay, you just, if you want to get the trigger, right? See, this is positive trigger. This is called positive trigger. Okay, so what did you get here? Due to this delayed input, what is the contribution of delayed input? The contribution of delayed input is this. You get slight, this is called positive trigger. That's called positive trigger. So if you want to get the positive trigger, then you can use this kind of delayed input. So that's the advantage of delayed input. Sometimes in digital electronics, you need delayed input, okay? So meaning because you want to produce some kind of trigger, positive trigger, sometimes negative trigger. So in that case, so you will see the use of this kind of trigger in the coming slides, okay? All right, so before I go to the next slide, let me talk about these things. So the TPD of NOT gate and AND gate is are almost same, and they are 7 nanosecond. So hence more than one NOT gates recommended. Remember TPD varies with temperature and from gate to gate. So if you wanna this, you know, this. So if you wanna get this trigger here, depending on what is the width of this trigger, right? Depending on the trigger width you need, you might want to use more than one NOT gate. That's what I'm suggesting here, okay? Now let's talk about the negative edge detector. So here, so this is also acting as the positive edge, because so this is your positive edge, right? See, so this at the positive edge you get the trigger right here. That's why this is also called positive edge detector. So similarly, you can do the negative edge detector. So how do you detect this negative edge, right? If you want to detect the negative edge, then you can have the NOR gate instead. So what did you have in the previous slide? You have a AND gate, right? This is AND. AND gates with 3 NOT gates here. gave you a positive edge detector. In the same way, the NOR gate with 3 NOT gates will give you negative edge detector in the same way. Okay, so I'm not going to talk about everything, but let me talk right here in this region. Okay, this is where negative edge occurs, right? So again, there is a delayed output. So delayed input, this is input, and this is a delayed input. And here, when at this location right here, you have, what do you have here? 0. What do you have here? 0. So what is the truth table of NOR gate? If you have 0, 0, what do you get? 1. Okay, so that's what we have here. So you can describe this in the same way, the way we did here. Okay, so we did this here in detail, right? So in the same way, you can get this trigger here. So when you see this kind of trigger, it means you have a negative edge there. Okay. So 7 nanosecond is short time, and it's roughly equal to 100 megahertz. At this frequency, capacitance, inductance, behavior of the wires also becomes important, because this is very short time, which is equal to this megahertz. Remember, we change it to frequency equals 1 over t. And if you plug in this t equals 1 over 7 nanosecond, then it comes out to be, your frequency happens to be 100 megahertz. So if you are talking about this short period of time, then not only the inductor, right? Suppose you have this inductor. Not only you need the inductor or capacitor to see the effect of inductance and capacitance. Even the even the wires at this time limit. I'm talking about this time limit. At this time limit, even the wire behaves as capacitance. It also behaves like inductance at this time limit. Okay, so if you are talking about this time limit, then you must use short wires, so that you wanna decrease the effect there, right? So unnecessary capacitance and unnecessary inductance, you don't want to see that. That's why instead of using long wires, you use short jumper wires. Okay, short jumper wires will eliminate this problem. Or you can use you can increase the time propagation delay. Okay, so if you have however, if you want to work within this short time limit, short time, then your wire, even the wire, right, jumper looks like behaves like a wave moving through the wire. Okay, so input looks like wave to it. Okay, suppose then there's one, it looks like wave, right? So it looks like wave, small wave. So any input looks like a wave, and also at the end of this, some of will be reflected back again. See, not only going forward, it also reflects back. That kind of reflection is called ringing. So when you come to the real world, there are lots of details you need to talk about, right? That's it's not easy. So you have to be very careful in the real world. So you have to know the propagation delay, then you might have to, if it is very, very small, then you might have to take into capacitance and inductance in the jumper wire also. Okay, so and also there will be ringing. There are a lot of stuff there you need to take into account. So this is real world. All right, so let's talk about the memory device now. Flip-flop So you have heard of, guys, any questions so far? I don't want to move quickly. Just I want to go slow. So any question so far? All right, so let's talk about flip-flops then. So the flip-flops. So first of all, let's talk about the 1-bit memory cell. So we know the computer we are using, right? We have trillions of, it talks about trillions and trillions of zeros and one, right? Okay, we have trillions of them. So we talk about, when you talk about computer, we talk about in trillions of zeros and one. But now I'm talking about just 1 bit. So that's basic, that's the very basic 1-bit memory cell. I'm not talking about trillion, I'm just talking about 1 bit. So how to store 1 bit? Okay, so that's the 1-bit memory cell. Suppose you have 2 NOT gates connected like that, right? So let's see the NOT gate connection here. So you have NOT gate 1, this is NOT gate. I call it and NOT gate 1, and this is NOT gate 2. So now this is A, this is B. A is connected to NOT gate 1 and B is connected to NOT gate 2. Actually, this A is the output of, actually this A is the output of B. Okay. So this kind of loop is called a feedback loop, by the way. Okay. When the output is connected to input, this kind of loop is called feedback loop. Similarly, here also we are connected to output connected to input. Okay. So this kind of device having with the feedback, this acts as a memory cell. Okay, so what do I mean by that? Let's see. So let me begin with suppose this Q has let's say Q is 0, right? So this device has, suppose you just turn this on, right? Suppose you just turn this device on. So, and this device has 0. Before you turned off, it was 0 here, for instance, right? Then this is 0. So when this is 0, what is this guy? 0. What is this guy? 1. Then what is this guy? 1. Then you get 0 here. So no matter what you do, you cannot remove this 0 here. You get this 0 all the time there. So we say Q equals 0 is last. In that case, we say, so 0 is last there. Similarly, suppose this guy had 1 there, right? If you started, suppose you have 0 here instead, right? So then this is 0, and this is 1, and this 1 goes here, then 1 becomes 0, this 0 becomes 1, and you always get 1 there. It means your 1 is last or locked. That kind of behavior is called memory behavior. So when you lock there, so when you have memory, right, what does it mean, right? Let's talk about human memory. So if it is there all the time, we call it memory, right? So this 1 is there all the time. So in that case, we call it memory, okay? So this can remember 1 or 0, depending on what you started here. If you started with 0 here, so you can see 0 less there. If you started with 1 there, then you can see the 1 less there. So you can somehow lock 1 bit there, right? So that's why we call it memory cell. So it has, you can see, so this can be either 0 or 1, right? If it is 0, it's 0 forever. If it is 1, 1 all the time. That's why it can have 2 states there. 0 states and 1 states. That kind of device is called 2 stable state device or bistable device, right?
Quick question, Professor. What would happen if A and B is like our inputs, right?
Well, in a sense, yes, but they are the output of the other, right? The output of the other is, we can say input, but they're actually the output of the other thing.
Okay.
Go ahead, go ahead.
Okay, so I think I'm getting that. So we actually set Q and Q naught, or not Q naught, but Q prime.
Yeah.
Those are the two that we're setting?
Actually, we mainly talk about the Q, but just in case, this is plan B, okay? So we most of the time we talk about Q, because if Q is 1, this Q prime happens to be 0. All the complement, prime is complement, okay? If this is 1, 0, then this becomes 1.
Okay, that was going to be my next question. So there's no instance that both could be the same.
If both are same, then we'll be in problem, and we'll have that problem and we'll solve it, okay?
Okay, thank you.
We'll have that problem in some cases, so we'll solve them. So when Q equals 1, right? When Q equals 1, that state is called set state. When Q equals 0, this state is called reset state. Reset, not rest. Reset. So when Q is 1, you will get 0 here. When Q is 0, you get 1 here, right? Okay. The thing is, you can lock 1 and 0, but you cannot lock 0 or 1 at will, okay? So whatever there is there. So that's the problem with this, okay? So whatever, suppose you have 1 here, you can lock your 1 there. If it is 0 there, you can lock your 0, okay? So that's why there is a problem now. So that's why this is not exactly, this is not, even though this is memory cell, technically this is memory cell, but this is not useful. Not useful. Because, so we cannot lock 0 and 1 at will, whenever you want. So that's kind of useless. So now we are trying to make the useful device, right? We know what might happen, but we know there is memory, but how to make it useful, right? So how to make the memory device useful? Means we have to be able to lock the information whenever you want. So the next device is called Arya flip-flop now. Hello, can you hear me?
Yes.
Okay. So this RS refers to reset set, okay? R refers reset, and S refers to set. So why do I call RS instead of SR? Because maybe it is alphabetical, right? P, Q, R, S. Maybe that's why we call RS instead of SR. Sometimes I see people calling SR too, but I call it RS, okay? Because this is alphabetical. So P, Q, R, S. So R is reset, S is set. So this is called RS flip-flop. or we call it Arya's latch. Okay, so in this case also, this looks like this. The Arya's flip-flop looks like this. So here you have input now. You have one input R, the other input is S. And the next input here is the output of the other one, right? See, it goes from here to there. That's the output, becomes input. And this output becomes the output input for the lower gate, right? So again in sequential logic, you will always have a feedback loop, okay? So you always have this kind of loop, which is called feedback loop. All right. So let's talk about Arya's behavior of this flip-flop, okay? So Arya. So how does it latch 1 and 0 here? This Q is sometimes 1. When if you wanna set, then this becomes 1. If you wanna reset, this becomes 0. Depending on you want 1 or 0, so you can do that, okay? So that's why this will be useful to you. So you can do that at will. So how? Let me talk about that, okay? So sometimes you can latch 1, sometimes you can latch 0 there. So let's start with set. Set state meaning you want to set means you want to latch 1, right? Okay, you want to latch 1. That's the set. Set meaning latch 1 at Q. So Q is your output. So in that case, if you want to set 1 here, oops, if you want to set 1, then what you do is you choose S equals 1 and R equals 0. If you choose S equals 1 and R equals 0, you can set 1 here. And then after you can latch. Okay, so let's talk about how do you set. First, let's talk about set, then we'll talk about latch, okay? Let's set this 1, then latch it there forever. So if R equals 0, S equals 1. So let's begin with S equals 1. You know why I begin S equals 1? Because I have the, what is this gate called? Help me here. What kind of gate is this? This gate is?
A NOR gate.
NOR gate, right? Do you remember the truth table of NOR gate? So in the NOR gate, what happens is, if one of the input is 1, the output is 0. If one of the input is 1, output is 0. If one of the input is 1, output is 0. So if one of the input is 1, output is 0. That's the beauty of NOR gate. That's why when this is 1, right? When this is 1, when S equals 1, this is 1, then I don't care this guy. So just hold on a second, okay, guys? I'll be right back. Yeah, what did you say?
Oh, I was just asking everybody how they're doing.
Oh, okay, good. All right, so where I was. So I was there. Where so help me. Yeah. Here, right? I was here. Okay, I started with S equals 1. Now, no matter what this guy is, X meaning it could be 0 or 1. Okay, that's the meaning of X. X means, let's say, don't care. X means don't care for now. Don't care meaning could be 0, could be 1. So no matter what this guy is, what is the input, what is the output here? Help me.
0.
0, right? So you don't worry about this because this is 1. That's why this 1 makes sure this is 0, right? So when this is 0, what is this guy? 0. Then this is already 0 because that's our choice, right? Our choice is S equals 1, R equals 0. That's our choice. So when R equals 0 and this guy is 0, then what is your output?
1.
1. So now this X is no longer X, this is 1. This is 1. Then 1 and 1 gives you this 0, right? There again is the same process again. So this 0 goes in here, and this is already 0. Then you have 1, you have 1. So you set it to 1. Okay? Now the thing is, you set this to 1, but you want to latch it. Okay? So what do I mean by latch? Let me talk about that. So that state is called hold state. Latch meaning hold. You want to hold this 1 there forever. So when you want to do that, you change your S to your S equal, what was there? You started with S equals 1, R equals 0, right? Now change your S equals, change this 1 to 0. In this case, what happened? S equals 0, R equals 0. Change 1 to 0. That's what I said, okay? Change 1 to 0. So you don't have to talk about this guy. You don't have to talk about this guy because you are not doing anything here, right? You just change your S from 1 to 0. 1 to 0. If you change your S from 1 to 0, then what do you get?
1. You get 1.
Where? Here?
Yeah. Oh,
Remember, this is 1. This is 1, right? This is 1.
that's, yeah, my bad.
This is 1. This is 0, right? So 1 and 0. Where is that? Here.
That's 0, yeah.
It is 0, right? So then this is 0. This is 0. Now this is 0, and this is 0. 0 and 0. 1. So this is last now. If you want to latch it, just change both of them to 0, 0. Both of them to ground. Okay, you set it here, set it to 1. If you want to hold this and change both of them to ground, then done. You hold the 1 there. Okay, so if you want to set, again, if you want to set, S is 1, R is 0. Now you want to hold it, put them both of them to 0. Then you hold 1 there forever. Okay, so you can latch your 1 there in that way. Okay, now, so what happens if you want to reset? So you had 1 there, right? Now you want to reset it to 0. So if you want to do that, if you want to reset and latch. Okay, so what you want to do? So if you want to do that, so change your R equals 1 and S equals 0. In the previous case, you had S equals 1 and R equals 0, right? So that's called set. This is set state. Set. Then this is called reset now, okay? This is reset. Let's see what happens. When R equals 1, S equals 0. S equals 0. R equals 1. Where do you want to start from? You want to start from top or bottom? You want to do, we want to talk about this guy first, right? Because, so one of them is 1, gives you 0, right? That's why if this is 1, no matter what this guy is, you get what? 0. This 0 makes this 0, and 0 and 0, NAND get 1. And this 1 goes here, this X is now 1. Then 1 and 1, 0. So you set it to 0, right? Now this is set to 0. And if you want to latch it, they change both of them to 0, 0 now. Okay. Now this R is already 0. Set this as to 0. From 1 to 0. You switch it back to 0. For now, both of them are 0, 0, meaning both of them are ground. Now, what happens is this will be 0 here forever. So how? Let's see. So now this was, oh, not this one, sorry, not this one. I should have said this one here, this to 0, right? So this is the previous case. Let me erase this. So let's change your R equals 0 to 1. So 1 to 0. So here, this is 1, this is 0. So this is 0, this is 1, gives you 0. And this is already 0. And this is 1, this is 1. So this 0 will be there forever. So when you have S and 0, both ground, right? Then it's there. Meaning, even though you have, meaning in the ground state, right? When you ground when you have 0 and 0, it's still there. When it is 0, when this is 0, then the thing we set there is there. Meaning, now you can use this guy for your, this can be useful now. So you can use this guy for your purpose. Because whenever both of them are 0, it's still there. Meaning it's the memory, it's still there. Guys, question here? Okay, now the thing is, now I'll go back to the, I'll answer the question that Emery asked me before. So what happens, now we talked about 0 and 1, we talked about 1 and 0, then we talked about 0 and 0 to hold it, right? So, but the thing is, how about 1 and 1? If you have 1 and then 1, what happens? Suppose R equals 1, S equals 1. So if R equals 1, irrespective of this guy, what do you get here? 0.
Yeah.
So what is this guy here? 0. So what is your expectation? You should get the opposite of this, right? So if this is 0, this should be 1. That's why we label them Q and Q prime. Prime means complement, right? If this is 0, we should expect here 1. But that did not happen. That's why choice of R equals 1, S equals 1 is illegal. And we shouldn't do the illegal things. So that's why S equals 1, R equals 0 is illegal. So we shouldn't do that. Now we have a problem here. So we have 1. So R equals 1, S equals 1 is illegal. That's the problem with SR flip-flop. Or RS flip-flop, right? RS flip-flop, that's the problem. So RS flip-flop is illegal when R equals 1, S equals 1. But we never know whenever you are going to change 1 or S going to change 1, right? We never know. It might happen anytime. So then how do you figure out how to exclude that thing then, right? That's the problem. We're a little excited because we can hold the thing, right? We can hold it, meaning even though they are 0, 0, our output is there. We're excited. Either 0 or 1. Not there. Here. Your output is here, either 0 or 1. But the thing is that there is one more problem here. We have illegal thing. So Q and Q prime, they are same, which is illegal. Okay, we should avoid that. So to avoid that, we have to modify this gate. We have to modify this RS flip-flop, and modified version of RS flip-flop is called D flip-flop. That D flip-flop does not have that problem. Okay, let me see how that can be done. Okay, so now for the in the D flip-flop, so by the way, so now instead of having this, right, instead of having this entire picture, so what I would do from now on is I just make this. How many inputs there? 2 inputs. How many outputs there? 2 output. Q and Q prime, R and S. That is how I represent this guy now onwards, okay? So I had this before, right? This is the SR flip-flop. Okay, RS flip-flop. This is RS flip-flop. Now how do I change it to D now? D flip-flop. I want to change it to D flip-flop. How? By adding NOT gate here, like this. Add NOT gate. This is exactly SR. Okay? Or RS. This is exactly RS. Now only change, only modification is you put the NOT gate here. You put the NOT gate and you call it D flip-flop now. Now what happens? Let's see how the D flip-flop works. What is our goal? Our goal is exclude 0, 1 and 1, right? We want to exclude this guy, right? Exclude. So now when this 0, D is 0, S is 0, R is 1. When D is 1, on the other hand, this is 1 and this is 0. You will never get 1 and 0. But the thing is, how do you latch them? You have another problem again. Okay, this is the 1-1 problem, right? We could exclude this guy, but the problem is, how do you latch? Okay, you set it to 1. Okay, now if you change it to 0, right? You should have 1 there. Set it to 0, you change it to 0, then it should be 0 there forever. But this is not going to happen because that condition never occurs here. 0, 0 never occurs. We cannot hold it. We cannot latch the data. We can set and reset, but we cannot latch or hold. So D flip-flop, we are a little excited, but it's not working as desired. Then we have to change some modification to the D flip-flop now. Okay, some modification again. That modification is to have the enable input again. So you have exactly same thing as before here, with one more extra input here. This is called enable. This goes like this, connected to both of them. And you have the AND gate here. That's the modification to this guy. 1 enable and 2 AND gates. Now this guy finally will work as desired. Let's see how. Okay, so let's see how. All right. So here. So whenever E equals 1, right? Let's begin with E equals 1. When E equals 1, your D is 1. It could be 0 also. First, let's finish 1, then we'll talk about this 0 also, okay? Let's do 1 first. When D equals 1, E equals 1. What is your, this guy? What does this give you? Not gate, right? This 1 becomes 0. See, this 1 becomes 0 here. Then this is 0, this is 0, right? This is 1. And how about here? This is 1. This is 1. What does this guy give you?
1.
1, right? This guy give you 1. And how about this guy?
0.
So when S equals 1, R equals 0. What is that condition? Set, right? S equals 1 means your Q equals 1. Keep that in mind. S equals 1 gives you Q equals 1. So it means we are setting, right? S equals 1 means set is on. Okay? Set is on. Means you get 1 here. Set is on, you get 1. So that's the meaning. So S equals 1, Q equals 1. So S equals 1, Q equals 1. So we are happy with 1 and 1, right? So 1 and 1 is done. 1 and 1 is done. We are happy. Because this is similar to S equals 1, R equals 0. This gives you 1. Now let's change my E to 1 and D to 0. What happens? E to 1 and D to 0. So now let's change it to so E equals 1. This is 1. So D equals 0. When D equals 0, what do you get here?
1.
1. So when this is 1, and this is already 1, this gives you 1, right? This guy gives you 1. Then what is this guy? What does this guy give you? This is 1. This is 0. This guy gives you 0. So S equals 0, R equals 1. R equals 1 means you are resetting. R equals 1 means reset is on. So when reset is on, meaning you get here 0. So we are getting here 0. Sometimes we are getting here 1. But the thing is, can we latch them, right? Can we latch them? That's the thing. Let's see. Can we latch? So our one problem is solved. We can set and we can reset. That is solved, right? Sometimes we have 1, sometimes we have 0. That problem is solved. The question is, can we latch them then? Let's see. Okay, so let's change your E to 0 now. To latch, we're gonna try this guy to set to 0. So this is 0. Now I wanna change this to 0. When this guy is 0, what is this guy? This is 0. Both of them are 0, right? Now whatever the value of D, see, whatever the value of D, it could be 1 or 0. What does this give you? This gives you 0. This gives you 0. So in order to latch, what do you need? What should be the value of S and R? Help me. What should be the value of S and R if you want to latch? You know, S should be 0, R should be 0, right? So that's happening here. So if you want to latch this guy, then your S equals 0, R equals 0. So it means we can hold also. So the problem solved. And 1 and 1 never occurs here, right? So if you have, this guy never have 1 and 1. This will never have 1 and 1. So that illegal thing also avoided. Okay, this output and this output can never happen 1. So that illegal thing avoided. And also we can set, we can reset, illegal thing avoided, and we can hold it. This is perfect. So,
Now, just a quick question. What does a hold mean?
oh, suppose, so the data you have this. So suppose, okay, suppose this is 1, right? So here. Suppose you have 1 here, right?
Right.
You're asking me hold.
Right. Like, what is I guess what I'm asking is, what is a hold used for, or what does the output look like?
Oh, hold means, oh, okay. Okay, I think, so when, okay, let me, okay, I think I can answer this question this way. So when E equals 1, D equals 1, let me answer this question based on this picture, okay? So when D equals 1, what did this give you? This is 0, and
Right.
this is 1, and this is 0, okay? When this one of them is 1, the other one is 0, you get 1 here, right? Now this is called set. Now you have the value here, right? So you want to have this value there now. You set it to 1. Now you want to have this 1. So how do you do that? In that case, you change it to 0. If you change it to 0, right? Then whatever your value here, look here, whatever value here, this doesn't change.
Oh, okay. So that's just like with the first one you were telling us that we could lock in a value. That's how we lock in a value with this.
Yeah. So you can send 1 and 0 here. So depending on what you want to lock, right? What you want to lock here, you send, if you want to lock 1, you send 1. Okay? So but your E should be 1. So if your E is 1, D is 1, you are getting the value 1. Now you want to lock this 1 there forever, right? Then what do you want to do? So why do I want to lock? Because this value, this data can change it to 0 anytime, right? But you want to have the 1 locked there. So you have the 1, you want there, you don't want to get it changed. Okay? It means, so how do you get that change? Now change this to 0. When you change it to 0, no matter what the input will be, your 1 is always there. That's how you lock it or hold it.
Okay.
If you don't hold it, what happens? If you don't hold it, then if it is changed to 0, this guy changes to 0 again, right?
Right.
So that's why if you want 0 here all the time, then you have to change this to 0 quickly. Change this guy to 0 quickly. Otherwise, depending on this data, this might change.
Okay.
Does it make sense?
It does. Thank you very much. I appreciate it.
All right, guys. Any other question?
Do you have office hours tomorrow in Beaumont or on Zoom?
Tomorrow.
You have what? I didn't hear you. Sorry.